Hi everybody, I'm Greg Fischel and welcome to bonus weather video number 1 for this Labor Day week. And today we're going to talk about something called vorticity, which is a fancy scientific word for spin in the flow of the air. And so we're going to talk about that, and there are actually several different ways that it comes about. So let's go on ahead and get into this now. And basically, what is vorticity? Well, it's rotation in the flow, but it can come about in 3 different ways. First of all, planetary vorticity is caused by the Earth's rotation. Curvature vorticity is simply a curvature in the flow itself. And shear vorticity is caused by differences in wind speed over a given direction. So let's dive into each of these in a little bit more detail. First of all, if you were to look down on the North Pole from outer space, the Earth rotates in a counterclockwise direction, and planetary vorticity increases with latitude. So at the equator, it's 0, and it reaches a maximum at the North Pole. Now, for those of you that remember your trig days, this goes along the lines of being proportional to the latitude, the sine of the latitude. So for those of you that remember this, 0 degrees, the sine is 0, and 90 degrees is 1. And so basically that's why it maximizes at the North Pole. Okay, now curvature vorticity, and I got to tell you, I spent about 2 or 3 hours trying to figure out how to get these little triangles to animate. Never did figure it out, so I apologize for the boring static image. But basically, you know that the winds blow in a counterclockwise manner around lows and a clockwise manner around highs, and so you can see why the flow would dip underneath the low and then ascend and go over top of the high. And so the flow is curved by nature of those two systems, and so that's what contributes to curvature vorticity. And then one other little mathematical note here, and this is for those of you that are just really geeky. You remember when you had the protractors, and as you closed it up like that and drew a circle, the circle was very tight and the curvature was significant. And then as you extended the protractor wider and wider apart, that the circle was much larger and the curvature was much broader. It wasn't as sharp. So curvature vorticity, the mathematical representation, is the speed of the wind divided by the radius of rotation. And so the smaller that radius is, the bigger V over R is, and the more curvature vorticity there is. And of course, as the radius gets larger, then the amount of curvature vorticity would actually go down. Okay, now let's talk about shear vorticity. Last but not least, supposing we have a low to the north, a high to the south, and we've got the jet stream in the middle. So the strongest winds are right in the middle of that area between the low and the high, and then the winds decrease both to the north and to the south. Because of that, these two blocks of wood, if you will, rotate in different directions, counterclockwise to the north of the jet stream and clockwise to the south of the jet stream. And so the shear vorticity is positive to the north of the jet, and it's negative to the south of the jet. And so the positioning of the jet stream is very, very important in terms of how the sensible weather ends up being at any one given location. So that is basically it for now. Hope you enjoyed that. Hope you found it educational. We'll have another bonus weather video for you coming up on Friday, and of course our regular daily weather update coming up tomorrow afternoon. And so we hope that you will stay tuned for all of that. And I guess it's just sheer excitement that is going to motivate you to do that. I apologize for that pun. All right, that's it for now. We'll see you tomorrow. Take care.